he will be talking today about something very provocative title, Cardiac Tissue Engineering, Fact or Fantasy. So thank you very much for coming.
So thank you very much, Angel. I've known Angel for several years, and some of the research I'm going to show you is in part collaborative with him. And it's also a pleasure being here today because there are many known faces from a professional point of view and also from a local point of view, since some of the investigators here are also from Vic, my hometown. So I am a cardiologist. So what a clinical cardiologist can tell you, I don't know. I'm going to try to explain the story where we've been working in the past 8-9 years, and let's see. So myocardial infarction is been our focus of attention. Right now, exactly last year, Herrick, for the first time, described the concept of myocardial infarction. So it's not such an old story. It's just 1 century old, 1912. And we recently published a paper dividing the story of myocardial infarction into 4 phases. 1912 to 1960 is an era of basically pathophysiology knowledge and understanding the process of myocardial infarction. Here we discovered that this is due to the occlusion of a coronary artery, and then we have a massive loss of cardiomyocytes which do not recover, do not renew, and this becomes a scar, a necrotic scar, that dilates the heart and leads the patient to heart failure and sudden cardiac death. So at this time, the only clinical therapeutic option for this patient was bed rest and low sodium diet. So that's it. This era, 1960 to 1990, it's the major breakthrough in myocardial infarction treatment and therapeutical approach. As you can see, the infarction becomes smaller. Why? Mainly because of the discovery of pharmaceutical treatments and surgical treatments. Among the pharmaceutical treatments, it is the discovery that aspirin is good for reducing coagulability. So antiplatelet therapy was discovered to be useful here. The use of beta blockades and the discovery of beta blockers, the discovery of ACE inhibitors, the discovery of thrombolysis for lysing the blood that obstructs the artery, and as you know, Favaloro in this time did for the first time a coronary artery bypass, which also improved survival and quality of life in these patients. And in these ages, the first heart transplant was performed. So this is these 3 decades are cornerstone for the treatment of myocardial infarction. In the past 20 years, what have we done? We have refined what we had in the past, and what we're doing right now is we're implanting, I'm not sure if you can see it here, yes, okay. We are implanting a stent in the coronary artery, and our aim today is to put this stent to open the artery, the so-called the open artery theory, is to open this artery as soon as possible. Nowadays, in Catalonia, we have what we call the CODI infarct. The CODI infarct allows the patient that have chest pain to go through an ambulance directly to the cath lab and to put the stent. And we are achieving this with relatively short periods of time. What is this accomplishing? That the infarct size is smaller and smaller. And as we get the infarct size smaller, the complications and the risk of death, which is the major complication of infarct, is gone down. So these patients survive the infarct, but nevertheless, they do have repeated infarcts. So now what we are seeing are patients who do survive quite well the first infarct, but then they have more often other infarcts. So for the future, we are planning 3 potential options to restore and remove the remaining scar that is here, which is cell therapy based on isolated cells of different etiologies and different origins and different lineages. We still don't know which one's going to be the winner here, ATDPCs, IPS, bone marrow, embryonics. However, because of cell therapy within the heart has not had a substantial benefit so far, a new approach, which is tissue engineering, is growing. And tissue engineering, it's basically using the cells but placing them in the area of the scar to replace the necrotic cells by new multipotent cells that may have the ability of developing into contractile cardiomyocytes. And also let me tell you about this gene therapy, which has been very criticized, but the group in New York by Robert Hajar is actually transfecting SERCA2 through the coronaries. And in the first pilot study, the CUPID study, they found some very interesting preliminary results, and they are moving now to a phase 3 clinical trial. So injecting a gene for SERCA2 into the coronary arteries. So this is where we are, and where we plan to go in the near future. Just a basic fact that you all know right now, 10 years ago, the heart was considered a terminally differentiated organ, and cardiomyocytes were considered to be living as long as the lifespan of the person. So until 10 years ago, the dogma was that all the cardiomyocytes that you had when you were born were the same cardiomyocytes that you had when you were going to die. Our group and others did some studies. We use fish to identify the Y chromosome, XY chromosomes in heart transplant patients. These studies were performed previously in small rodents, but in humans, we were some of the first to identify that when we transplant a female heart into a male receptor, we, after a while, identified male cells within the female heart. We did the opposite experiment, transplanting a male bone marrow into a female receptor, and we were able to identify male cells within this female heart. And this is the story of chimerism of the heart. And also we did some studies of fetal microchimerism. We know for a while from immunology studies that fetal cells may cross the placenta, get into the maternal circulating system, and eventually colonize and transdifferentiate into different organs. What we found is that in studies of patients that were undergoing heart transplant, so we removed the heart because of a dilated cardiomyopathy, who had had story of previous labor of male offspring, at least one male children. We looked for this heart, and we did identify male cells within this heart which were immunologically compatible as far as HLA measurements with the son. So there are cells that are able of crossing the placenta. These are progenitor fetal cells that go into the circulation and colonize the heart. So this is a concept that nowadays is quite accepted, and there are now other recent studies using survivors from the Second World War II, which are telling us that approximately 50% of the cardiomyocytes of our heart are going to be removed during our lifespan. So this is a process that happens in a very small amount, so one by one can be removed. When we have a massive loss of cardiomyocytes, this process of removal in humans does not happen. In zebrafish may happen, but in humans it doesn't happen. So nowadays, what's the real situation that we believe is that cell loss and myocyte proliferations are part of the heart normal homeostasis in humans, and therefore there is some degree of auto-regeneration which is limited, and it's probably limited to a cell-by-cell phenomenon, which it has not yet been completely deciphered, and there is some research into that because we do not know yet which is the trigger for an individual cell to home into the myocardium and eventually transdifferentiate to a cardiomyocyte. And therefore cell therapy and tissue engineering may emerge as efficient and safe therapies. So once we know this, there was a huge career from clinicians to be the first to treat patients with cells and get the Nobel Prize. I mean, that was the goal. And it was crazy because there have been so many millions of dollars spent in studies that had not had a basic rationale or a solid rationale to perform them. And as you will see, some of these studies have not gone anywhere. So after 10 years, we have had to go back and do some of the basic research. Let me start from down up. Stem cell mobilization with cytokines, particularly GCSF. So if the heart can repopulate from progenitor cells, and these cells come from the bone marrow, what if we stimulate these stem cells from releasing the bone marrow into the circulation, and eventually those will home into the heart. Well, that was an attractive idea, because if this was true, anybody in any hospital, irrespective of the technology, could do this. This was a failure. So the Revival 2 study showed that this is no good. You don't do anything to the heart. The ejection fraction, the contractility is the same. What about if we use myoblasts? Myoblasts are progenitor cells that we found in skeletal muscle. Easy to isolate, easy to culture, easy to obtain. Interesting approach, very appealing. The issue is that when you put a myoblast into a contractile heart, this myoblast becomes a myotube, which contracts independent from the rest of the heart. So we're having arrhythmias, some of them lethal. So these patients had a higher risk of sudden death due to lethal arrhythmias. And in this case, we had to put defibrillators to a patient that was receiving a myoblast that was not improving his contractility. So at the end of the day, we're doing more harm than good. And that's just opposite to what the doctor has to do. What about intracoronary delivery of stem cells, either bone marrow cells or circulating progenitor cells? There are several trials in acute myocardial infarction, in chronic myocardial infarction. These are the major journals. There are many more in lower impact factor journals, but just to let you know that there are a number of manuscripts published in a high-ranked journals which have been completely discordant and have not reached a consensus about benefit. The BOOST trial was a preliminary trial published in 2004, was sold as a positive trial. Why? Because in the control group there was an increase of 0.7% in ejection fraction. In the bone marrow group there was an increase in 6.7% ejection fraction. That was considered very much, very positive, statistically significant. What about from a clinician point of view? From a clinician point of view, an ejection fraction of 50% after an infarction is a very, very low risk patient. So do I have to do a bone marrow aspiration while the patient is completely anticoagulated to isolate these cells, culture the cells, and then go again into the femoral artery, put a catheter into the heart to inject the cell? That's not going to do any good as far as clinical response, because these patients are doing very well clinically. That's my first concern. At the end of the day, these patients did very well, and there was no benefit after 12 months of this therapy. So it was positive statistically at 6 months. The statistical significance was lost 6 months later. So this was a positive trial. The same approach, the same design by Janssens 2 years later in the same very good journal, a negative result. So we are starting to have contradictory results. With all the therapies that I told you before, statins, ACE inhibitors, beta blockers, aspirin, all those were repetitively reproducible and with the same positive results. Here we are having one positive, one negative result with the use of bone marrow cells. This is a Norwegian study. We found no effects of intracoronary injection of autologous mononuclear bone marrow cells. In the New England, this is a German study. Bone marrow cells is associated with improved recovery of left ventricular contractile function. So as you can see, there's one in each side, and when you have positive studies and you look at them, whether this is going to have a clinical impact in my patients, here we are having an increase of 2.5% in ejection fraction, and 2.5% in ejection fraction by angiography is the degree of variability that we have in two different measurements. So that's a very surprising issue for us. So taking into consideration all these previous papers, and if you have in mind the physiology of the heart, which is that it's a pump that it's pumping the whole blood. Whenever you're injecting a solution in the coronary arteries, this solution, if it doesn't home within the first or the second heart cycles, all this cell suspension is going to be redistributed throughout the body, and it's not going to stay where you want it to stay, which is the scar area. And the scar area is a very dense collagen area where if you want to introduce cells into that area, you probably will need more time and some triggering signals to attract these cells more than a single or two single beats, which we're talking about 1 or 2 seconds. Okay? So we start to consider the fact that maybe we're not going to deliver solutions or suspension of cells. Forget the kind of cells. I'm not interested right now in which is going to be the cell, but we are not going to deliver cells, but we are going to deliver what the heart needs, and the heart needs muscle, and the heart needs blood vessels. They need contractile structures and blood vessels. And then is when the cardiac tissue engineering approach starts to get into this way. We need cells, whichever cells you want. We need scaffolds. They may be natural, synthetic, vascularized, non-vascularized, combination, biocompatible, biodegradable, partially biodegradable. These are the issues that you guys know more than me. And we need signals, because probably we're going to deliver cells that are not completely differentiated as true cardiomyocytes, but we probably may want to deliver cells that are progenitor cells committed to a cardiomyogenic lineage. And then once in the local contractile myocardium, they may eventually become the true cardiomyocyte. Because we have done many mistakes in the past, I believe that for all of us to go into the clinical arena, we are going to be able to create structures that are functional and vascularized, and they follow the GNP-GLP guidelines, that they are useful and they have a therapeutic value in small and large animal models. And once we have these, I believe it's the time to go to clinical trials. And from a clinical point of view, from a cardiologist point of view, the aim of my research is to try to get a product that eventually goes into the lower left corner of my first slide, which is where do we go from now to the future. This is a summary of several options that have been tested in tissue engineering for heart muscle. When you see a slide with so many options, you easily recognize that there is no valid one. They have all been tested. They have all have some positive and drawbacks. And let me go through some of these with you, with some of the positive and negative aspects that I understand, and then we may discuss. One of the pioneering groups is that from Thomas Eschenhagen in Hamburg. They did a culture of cardiomyocytes, neonatal cardiomyocytes in these agar plates, and these neonatal cardiomyocytes became these rings that they subject to these mechanical forces, and these rings, which is this is a ring of neonatal rat cardiomyocytes. They put 7 or 8 of these rings together into this mechanical structure into the petri dish until they fuse, and once they are fused, they suture them in the apex of a rat that has had a myocardial infarction. The proof of concept of this study is interesting because they proved that these engineered tissue grafts, they interact with the underlying myocardium. They adjust correctly, they synchronize their contractility with the underlying contractile function, and they increase the contractility of the myocardium of this rat. Moreover, after several weeks implanted, these cardiomyocytes remain the typical structure of a mature cardiomyocyte. So as a proof of concept, it was very interesting. For me as a clinician, I'm never going to use this. I'm never going to use neonatal rat cardiomyocytes for my patients, nor human cardiomyocytes. So I'm using this as a proof of concept that eventually, sometime, we may develop a tissue graft with a different kind of cells, with a different kind of matrix that may be useful. The group of Japan, Idezo Mori, what they did is very appealing and it's interesting. They cultured mesenchymal stem cells in a petri dish which is thermosensible. So whenever we change the temperature, you raise it or you lower it, these membranes just detach from the bottom of the petri dish. And when they did this in the state of confluency, these cells generate a self assembly of extracellular matrix. So we have this monolayer of cells with their own self-extracellular matrix, and they had this structure that were able to implant in the apex of a rat, and you have this monolayer of cells implanted in the apex of a rat, and they said, well, there is a perfect attachment of this new structure which has some benefit effects. So again, this is interesting. The same group is now trying to put several layers of cells, one on top of the other, the issue is hypoxia. I mean, this, as we said in the beginning, these cells need oxygen, and when you put them in a scar area, the degree of vascularization is very low, and they have problems with the hypoxia of the construct. New issues that are currently being investigated. The group of Lior in Israel is deploying alginate, simply alginate into the scar to see if just by implanting a product that is a scaffold structure may be vascularized, and this is going to help. They did these studies in the swine model post-infarction, and they found a preservation of the left ventricular area and increased scar thickness. What is more interesting is that the group of Bob Langer in the MIT, they said, well, maybe alginate alone is not the best option to go, because when you put cells into the alginate structure, they have these cellular compartments whereby the cells, they do activate in small compartments that generate electrical activity in different directions. So they nano-wired the alginate in such a way that these cellular compartments were all connected, and the electrical activity was following a path that would be compatible with a myocardial contractility. So this is an interesting approach of engineering the scaffold with nanogold and implanting the cells inside this modulated nanogold alginate scaffold. I'm not going to talk too much about the issue of Doris Taylor approach, because you probably have heard it, because it had a lot of media attention. In truth, this is not tissue engineering, because in truth, what they are doing here is a complete new organogenesis. It's not trying to cure a part of the heart. What the Doris Taylor approach is trying to do is to put a new heart. So remove the old one and put a new one. How do they do that? They take a heart, and by a system of Langendorf, they remove all the cellular structures in this heart to maintain the scaffold or the architecture of the extracellular matrix of this heart intact, without any cells. After they do this, they provide through the Langendorf system vascular progenitors, myocardial progenitors, and they aim to achieve a new contractile heart with different cells using the skeleton they have had before. As I said to you, this was published in 2008. It's 5 years from now. There's many research going on. It's not so easy, and the things are there right now. A lot of doubt whether this is going to become or not a real solution. But in any case, the journal Time magazine in the New York, in the USA, they already sell this story some Christmas ago, and they would say, why don't you buy a heart for your husband this Christmas? And they say, you keep the extracellular matrix in the refrigerator, and whenever he has a heart attack, you take his cells, you put them into this matrix, and you're going to have your heart removed, and it's going to be like a piece of a Lego. Yeah? Any case, Doris Taylor said, we are a long way off creating a heart for transplant, but we think we have opened a door to building any organ for human transplant. This was followed by Karen Chrisman recently using myocardium that was decellularized, and they milled this structure into a powder that was solubilized, and what they are doing now is injecting this extracellular matrix into porcine heart with some preliminary results that suggest that this is an alternative way to go. And in any case, a word of caution, biomaterial alone may not be sufficient. So some groups are thinking that just implanting biomaterial, some extracellular matrix, we are going to do well, and this is PEG hydrogel with saline. The remodeling of the myocardium is the same with one and the other. So biomaterial alone, it's not going to work. The only clinical trial that has phase 1 published results is this one by Chags in Paris. This is a human heart with a cardiac bypass, and on top of this bypass you can see a collagen matrix seeded with cells implanted on the top of this of the surface of this heart. There was benefit in end diastolic volume and scar thickness in treated patients. So at the present time, when we started the talk, is this a fact or fantasy? In a way, since we have already a phase 1 trial, it's fact. But is this a fact that can be routinely used in our everyday practice, that's yet to be completely demonstrated. Our group started to work several years ago with adipose tissue progenitor cells, and we initially obtained adipose tissue from the subcutaneous tissue, particularly from the subcutaneous tissue of the sternum in patients undergoing cardiac surgery, and we were able to isolate these cells and identify the properties of these cells. Due to a process that I would say it's more of serendipity than intentional, we started to look into the fat tissue that surrounds the heart. We realized that the heart contains a lot of fat tissue, and we started to look whether this fat tissue that surrounds the heart, that beats and receives electricity together with the heart, may be different to this subcutaneous fat tissue. And this is what we found. We did this research in collaboration with Angel some years ago. We found that the two origins contain mesenchymal stem cells, but interestingly, those progenitor cells that were obtained from the heart express GATA4 tremendously high as compared to those that were coming from the subcutaneous. And you know that GATA4 is an important transcription factor in the embryological process of cardioblast into cardiomyocyte, and therefore we thought that this was an activation of the genetic machinery of these cells that would put them prone towards a cardiomyogenic lineage. We did immunohistological studies, we did some Western blotting, we did co-culture. Here you can see that when we compare subcutaneous with cardiac progenitor cells, cardiac cells, under basal conditions, they express connexin 43, they express GATA4, they express alpha-actinin, they express SERCA to more or less the same level, and beta-myosin heavy chain. So these cells express all the proteins, almost all the proteins, except troponin, that I need to create a cardiomyocyte. What's most important is that when I put these GFP cells in co-culture with a cardiomyocyte, these cells quickly adapt their phenotype and express troponin. So here is the troponin expression of these cells that was negative under basal conditions and was easily expressed once co-cultured with the cardiomyocyte. So what we think is that the contact of these cells with a cardiomyocyte modulates the phenotype towards a more mature cardiomyocyte structure. These were the clinical studies, or the animal studies that we performed. Here, a rat animal with the scar, and once treated with these progenitor cells, the size of the scar was substantially reduced. And here, a mouse with a scar. This is a massive scar that is removing 50% of the contractility of the heart when we implant these cells. As you can see, the wall is much thicker and the area of scar is substantially smaller. So the next step, as translational researchers that we thought of is, are we always going to obtain fat progenitor cells by doing sternotomy and then putting them into culture, or is there an alternative way of obtaining these cells? So we were thinking of a surgery whereby we would isolate these fat pads like this. We would remove the pericardium, and after an infarction we were wanted to study whether these vascularized fat pads rich of progenitor cells with a cardiomyogenic trend would be of any use. So these are the experiments we did. This is already in a pig model, 45 to 50 kilos. The heart of a pig of 50 kilos is like a fist, is this big, pretty much similar to our hearts. Therefore, what we have here is the lung and the pig heart. We are isolating this fat tissue. We open the pericardium, left atrium, left ventricle. You have here the area where we put a ligation to obtain a transmural myocardial infarction equal to what we have in humans, and we displace this fat pad on top of the infarcted area to see what's going on. One way to analyze the effect of any therapy is functional. And what we did here is to assess this using the newest technology that we have, which is MRI. And with MRI, we can inject a contrast, which is gadolinium. And with gadolinium, we can see here in the control patients or in the control pigs that the lateral wall is completely white. This means that there is a full transmural myocardial infarction in our control animals. What about the treated animals with the fat pad on top? After 30 days, which is equivalent to 6 months in humans, as you can see, the infarct size is substantially smaller, very much substantially smaller. When we do MRI, we can reduce, because of the exactness and because it's almost anatomy, we can reduce the number of experiments to 1/10 of what we would do if we were doing echo. So with a smaller number of animals, we were able to identify very reproducible results. And as you can see here, there was almost 90% increase in ejection fraction. This animal with 38%, if this was a human, this is an important infarction with the risk of developing heart failure, with the risk of sudden death. And this is a patient that I need to follow closely in my heart failure clinic and probably to put a defibrillator, which costs 23,000 euros. This is a patient of very low risk that after discharge can be followed safely by a general practitioner and by any means needs any defibrillator. So we have here a potential approach that we were happy with this functional result. Why would this happen? We sacrificed a series of animals at day 6 and day 13, control treated with the fat flap, control untreated. As you can see from the very early days, this was a massive hemorrhagic necrosis here, much lower in the treated animals. In the controls, you have a very dense and mature scar with the trichrome staining, the mason staining. You can see that this is pure collagen, wherever in the treated animals there is much less collagen and there's a lot of surviving islets of cells. And as you can see here, in the middle of this scar, there's a full contractile pack of cells. Why would this happen? We did a series of microarrays from the myocardium and from the adipose flap, and we reached the conclusion that the adipose flap, which was, as you remember, a vascular structure, generated a great angiogenic response, and this great angiogenic response interacted with the myocardium, and hundreds of connections between the flap and the myocardium were obtained. This is not a bypass where you put a highway. These are small connections, but in a series of additional experiments, we found that between the flap and the myocardium, underlying myocardium, there was migration of stem cells from one part to the other. So with these results in mind, as I tell you, this was a preclinical animal study. We did over 50 animals, and there was safety because all the animals arrived to the end of the experimentation. We went to our clinical ethics committee to try to do clinical trial, and they said there are no ethical issues. And they say, we went to the surgeon, and the surgeon said, there are no technical complications, you can do this. And most importantly, there were no economic issues, so we could start as soon as we had all the permissions. So we are currently performing the phase 1 clinical trial in patients in Universitari Germans Trias. 50% of the patients have already been recruited, and they have been followed. The first patient already finished the first year follow-up and has done at the present time quite well. What are we doing? We are taking patients candidates to coronary artery bypass grafting. So these patients need to go to cardiac surgery because they have ischemia and they have to get a bypass in one or two of their arteries. But at the same time, these patients have a chronic scar that you would not do anything. And in this chronic scar, normally we don't touch it, and we leave it alone. We just put the 2 bypass in the other areas, and we leave this scar alone. We randomize our patients into the CABG alone, plus CABG, plus flap in the necrotic area. We're doing now follow-ups, and the idea is to do baseline MRI to these patients, and then 3 months and 1 year. Gadolinium is so sensitive that right now it can allow us to identify the grams of myocardium in grams that we recover with this therapy. So gadolinium reduction if this is going to happen. Actually, I am the clinician following these patients. I'm blind, and I cannot tell you how things are going. But if this is going to happen, the grams of gadolinium that we reduce with this treatment, they are going to be identified here. So we are going to know how many grams of cardiac tissue we have regenerated with this treatment. Anyways, we believe this is an interesting approach, which is the one here. But taking into consideration what I told you before, and the advantage of extracellular matrix and delivering more cells than just the ones that you have in the fat flap, we are now in a more advanced engineering approach, which is putting a decellularized matrix full of cells, covering it with the fat flap, and trying to create a bypass of this scar. So eventually what we are going to get is a contractile area here that may bypass the full contractile scar. It is plausible and conceivable that this very dense chronic scar may not be completely repopularized or recovered for contractility. Then we provide this slice of decellular myocardium with the progenitors that we decide, and we're going to try to see if we can do this bypass in the scar. At the same time, we're working in the this is a European 7 Framework Program, European Union project in collaboration with IQS, Carlos Semino, Monleon for biomaterials in Valencia, Juan Carlos Chaks in Paris, he's a cardiac surgeon, and Fraunhofer, they are molecular biologists, and they have these 3D bioreactors for culture of cells. What we're doing here is to create an elastomeric membrane that is developed artificially by Manuel Monleon by electrospinning of membranes and designing exactly the size of the pore and the characteristics of the pores that we want, which try to mimic the extracellular matrix. And then with a nano hydrogel, which is RAD I16, that's provided by the group of the IQS, we fuse these cells with the nano hydrogel into this scaffold, and we're trying to obtain contractile structures to deliver on top of the necrotic scar. I have to tell you that we have not been able to make these structures contract ex vivo. So far we are implanting these constructs in the animals, but in vivo, ex vivo, they have not been contracting so far. We label the cells, and by bioluminescence we have tracked these constructs in the mice model. As you can see here, we deliver these constructs appropriately in the right place. When we sacrifice the animal, the construct is completely attached to the surface of the infarcted area, and these constructs contain red labeled cells, and it's not easily seen here, but some of these red labeled cells migrated from the construct into the myocardium. These are work in mice that's just being finished, and just let me tell you that we have experiments in sheep ongoing. We have already performed 10 sheep with the delivery of this construct, and these sheep have lived now for 4 months with the construct, and after 4 months we sacrifice the sheep. We have done 10 animals, and the results are very good as far as benefit in contractility and reduction in the cavity size. One of the things that we have been working with colleagues from the UPC, and particularly Ramon Bravos, is in this electromechanical stimulator. We feel that the cells need to be delivered partially committed to a more cardiomyogenic lineage, and what the heart has is electricity, mechanical contractility, and biological products. So what we do here is try to mimic in the lab a structure that delivers electricity to the same pulses with the same amplitude and the same heart rate that would happen in vivo. This structure delivers a stretch of these cells by 10%, similar to what we have in vivo in the heart, and this structure in the petri dishes that we culture, we can deliver all the growth factors that we desire in order to achieve this cardio differentiation. So we have just recently published the effects of electrical stimulation alone, and we are just working in the combined electromechanical stimulation to finish with electromechanical and biological stimulation in order to get a cell that has already an environment that's very close to the one that's going to find when we do the tissue engineering approach. Finally, let me tell you about this smart patch concept that we do with the group of Jesus Uson in Cáceres. In this smart patch concept, we combine a biological membrane with the peptide hydrogel, with cells, an implantable electronic system, and nanogol. So we have a membrane. In this case, we obtain the pericardium, human pericardium, that we decellularize. We obtain also cardiac progenitor cells, the peptide hydrogel that we, RAD16, that we already used in the previous study. Nanogol, because it's a very it's a very important structure to improve the electrical current through the patch. We were interested in understanding the electrical currents that go through the patch. And with the group of Ramon Bravós in the Polytechnic University, we developed this electronic system. And this electronic system is the change in impedance within the 3D structure. What we know is when the cells change their phenotype from undifferentiated towards a completely cardio-differentiated phenotype, the impedance characteristics vary. And we have done this in 2D cultures, and this has been quite well demonstrated, and we want to demonstrate whether this is going to be a useful in vivo measurement of the process of cardio regeneration. So this is the smart patch. We have a scaffold, we put the nanogol, the electrodes at a predefined distance. This will lyophilize and then we rehydrate it, we put the cells inside, and we do the experiments with pigs. So what we do here is, this pig has had a myocardial infarction. We put this structure which has the electrode. The pig has this thorax, let me say it in Spanish, quilla, no? The thorax of the pig is more triangular, it's not so flat like ours. So when we close the thorax, if we leave this electronic system in the thorax, the animal just rejects, and by scratching against the walls, we would have problems. So what we did is tunnelize the electrodes and keep the electronic system in their back. Here is what you have. We're finishing the surgery. This animal is in Cáceres, and this is the antenna, and Ramon Bravós is measuring the effect of this patch every 10 minutes, just a little bit far away from here in the Polytechnic University. So we are getting measurements every 10 minutes online of what's going on in this patch. A number of experiments have been performed. I cannot tell you right now the conclusions because we are analyzing these electronic structures, but as you can imagine, working with pigs is not so easy. So when we went to sacrifice these animals, we removed the systems from all of the animals, and there was one that was missing. And if it was not in place, it had to be somewhere around, and it was not on the floor. So we had to do a complete autopsy of the animal, and it was in the gastric cavity, in the stomach. And this is what we put before, and this is what we obtained after. So pigs don't like to get messed too much, you know, and you need to make sure that you don't show them anything, because they will eat it. So they just eat anything. In any case, the group of Ramon they are so optimistic that we like to work with them, because they are still trying to get information from this. we will see. This is the first impedance measurements to monitor regeneration in vivo today. So maybe in the near future we can show you some of these results. And just to finish, just let me tell you that bioengineering a heart is a puzzle, and we have a long way to go. We're just starting to understand what's going on. And I understand that there are 4 major barriers that we'll need to overcome in the next years, which are ischemia hypoxia of the graft. This graft needs to be vascularized as soon as possible, or the graft needs to contain already vessels. Inflammation of the graft, so the process of rejection. If it's an autologous graft, that may not be the case, but inflammation is something that we need to consider. Intracardiac fibrosis, mostly the fibrosis would come after inflammation, but these are issues that we need to consider together. And graft survival has a lot to do with ischemia hypoxia. If we don't have vessels, we're going to have poor graft survival, and the cells of this graft are going to die due to apoptosis. So this is where we are, and I think we all here face the same issue. You may have a good idea, and you start doing basic biomedical research, and you may get some money some funding to do this, and you're happy, and you're in the high wave. When you finish your first results, try to go into the clinical science, you get somewhat depressed. If things don't go too bad, you get a little bit more money, much less already, and then the second valley is the hard one, because it's when, and it's the most important one, which is trying to translate what you understood in the basic lab into a clinical practice guideline and health decision making. So our aim at the end of the day would be that eventually the cells that we identified that developed into a surgical approach could be someday a surgical solution for all those patients with these characteristics, for instance. In any case, in cardiology, imagine in many other areas, this is Eindhoven. Eindhoven discovered the electrocardiogram in the 1901, and this was an electrocardiogram in 1901, and he said, I can register the heart, the electrical activity of the heart. He was completely criticized, and all his peers said that he was just crazy. He was having fantasies. And he said, I don't care. What you or I think is not important. What is important is the truth. So I believe that in this area it's absolutely the same. I'm not sure our approach is going to be the one, or another one is going to be the right one. Let's look for the truth, and then we will possibly get into the right direction. This is the team that has done all the work, and just the cheerleader. And thank you very much.